Hello, everyone. This is Mohammad. I'm coming from University of Southampton, Denmark, and the topic that I'm going to present today is about the effect of heat treatment on the mechanical property of like the stainless steel and nickel-based alloy 625 fabricated by additive manufacturing. Additive manufacturing by nature, so as we know, has different advantages and also disadvantages, and it has different technologies. And the technology that we use in this work was laser powder bed fusion, which involves the melting and solidification of metallic powder layer by layer in order to have the final product. And there are different parameters that we can categorize them by, for example, laser, in-process, pre-process, build, and powder parameters. And each one of these parameters affects the parts quality, either the microstructure or, for example, the surface quality and so on. Previously, what we evaluated, for example, the spot size, diameter, and the laser power in a previous work. We also evaluated the scan pattern in a layer, scan speed, layer thickness, also build direction in order to characterize mechanical property of produced parts for different alloys. And in this work, what we did, we only focused on scan speed and layer thickness. So other process parameters were kept fixed for different cases, and we only changed scan speed and layer thickness. And we used an exact metal 3D printer with a table dimension of 200 by 200 and also in a height of 120 millimeters. And we produced 81 specimens. So as we can see here, so we changed printing speed or scanning speed from 1400, 1700, and 2000 millimeters per second. And we changed for each case, we changed layer thickness. And we kept printing power and actual spacing for all the cases. So in that case, we produced 81 specimens only for doing heat treatment, plus 27 specimens for as-built characterization. So to compare what's the effect of the heat treatment on this case. And the heat treatment was done using a furnace, as you can see here, with the capacity of having a temperature up to 3000, but because of using the specimen, like the box that we had to put our samples, the maximum capacity was lowered to 1200 only. So we couldn't go beyond 1200, while the furnace itself had the capacity of 3000. And then we used the argon atmosphere for the heat treatment, for the process of heating up to the samples to the maximum temperature. And we used air cooling for doing the cooling process. Then the process was for stainless steel. So we had 3 different cases for stainless steel, 316O, temperature of 700, 900, and 1100. The time was 2 hours, so maximum temperature. So the heating of rate was 7.5 degree per minute, and the cooling was 2.5. And for Incolor 625, we also had 3 cases for heat treatment, 900, 1000, and 1100. We had the same. So we had the 2 hours for the maximum temperature, and then it was furnace cooled down for different different kind of duration based on the each heat treatment cases. As I said previously, we changed other kind of process parameters such as layer thickness, scanning speed, and so on. And in those studies for as-built samples, we saw that increasing layer thickness or scanning speed negatively impact the material property. And the main reason is about, as the previous talk mentioned, is about the energy density. So we know that the energy density, so we have laser power as the numerator, and layer thickness, scanning speed, and also hatch spacing in the denominator. So if we increase the layer thickness or scanning speed or hatch spacing, we are decreasing energy density. And that affects the mechanical property because we are destroying like the kind of the melting and the solidification to have a kind of a uniform formation of the part during the process. And that in the previous study, we saw that even in the literature, we can find this. So it's not, they were not the only like the group doing this, right? And as we see here, so these are the stress strain curve only for these two alloys for as-built. So just to obtaining initially, and if you follow the standard ASTM E0822 to do the simple tensile testing, right? And we used a kind of a simple tensile test, a universal tensile test, and using extensometer to obtain accurate strain. And for heat treated, so just an example of a stress strain curve. So for the case with layer thickness of 30 micrometer and a scanning speed of 1400 for the stainless steel, we can see the effect of heat treatment. So as we increase the heat treatment temperature, we can see we have a better ductility but reduce the strength. This is in accordance with what we see in the literature as well, and this is mainly because of the change in the grain size and also dislocation. So when we do the heat treatment, recrystallization is happening. So of course, at different temperatures, not the case that we see the same recrystallization order when we do heat treatment at 700 and 900 and 1100 is different, but we see recrystallization in different order, and also the reorientation of the dislocation, decreasing of the dislocation, and that affects in the reduce of the tensile strength, but increase in the ductility of the material. So we can see here, for example, if we from 700 to 1100, we see the decrease in UTS, ultimate tensile strength, but we can see that the heat treatment itself, we had almost a better kind of UTS in some cases, but other cases was almost the same or no differences, big differences. But when it comes to kind of elongation, as I said, we see that by going to upper temperature in heat treatment, we see a better ductility behavior from the material. And we saw the same, almost the same behavior for Inconel 625, the same effect, again, increasing temperature. We didn't see that yet. Moderately, like a small effect on the UTS, but kind of a visible effect on the ductility of the material. And if we look at only one case, for example, if we look at only for the 700, we can even see the effect of the single process parameter as well. For example, this case refers to layer thickness of 80 micrometer and the scanning speed of 2000, which the quality of the part should be lower, as we can see here. Even the literature forget the heat treatment, even just as built. It should deliver us the worst kind of mechanical property, ductility, and also UTS, as we can see here as well. So the trend here follows the as-built even for a single case, and so on from 700 to 1100 again is because of the older recrystallization, formation of the grain, like the kind of size of the grains, and also formation of the grain boundaries, bigger grains and then the smaller grain boundaries, and then also the kind of in one cases room for dislocation to move better, so the better ductility in that case. We also did hardness testing, and hardness testing we also saw same behavior. So in case of 700, we had better hardness, so we applied Rockwell hardness testing here, and we saw that in the 700 we saw a better kind of hardness when compared to others, but lower than the as-built. And this is also in accordance with what we see from the literature. So mainly when it comes to hardness, again, grain sizes and this recrystallization are the main factor affecting the hardness of the material. And that's the reason why we see smaller hardness when we compare to the as-built samples. Another factor, as just generally speaking, is that the porosity level as well. So when we talk about different kind of process parameters, for example, layer thickness or the scanning speed, we can see, for example, when we increase only the layer thickness while keeping the scanning speed, the porosity level increases. This is just for getting the heat treatment. And that's one of the main reasons, porosity, when it comes to additive manufacturing. And we know that the porosity is there. Of course, with advancement in technology, we see that the new machines are arriving that the level of the porosity gets smaller and smaller, but it doesn't mean that we don't have any porosity. As based on my knowledge, there is no machine producing a part with zero, almost close to zero porosity. And when we increase scanning speed while keeping layer thickness constant, again, the porosity level increases as well. So that, again, this is exactly what defines energy density. Again, increasing scanning speed, increasing layer thickness decreases energy density. And if we have a decrease in energy density, it means that we are going to have not having a uniform melting of the material, right? And that's the case. If you have a higher layer thickness, it means that if we have the same energy density, we are not going to have remelting of the sublayers and better bounding between two layers, right? So that's the reason why we have a kind of less UTS or strength for the materials with a higher scanning speed and layer thickness. And unfortunately, because of some technical problems, we couldn't use our XRD device, and we plan to use it and present what is happening at the grain scale and the microstructure, but we couldn't use that because of some technical problems. I hope probably in the next in September we can use that to better connect microstructure, like the formation of the grains and so on, to what we saw from the macromechanical testing. So literature, for example, says again, the crystallization, grain growth, and so on, the reduction in the dislocation. What we wanted to see in our cases, is it the case? And mainly to obtain the optimum temperature for the heat treatment. We test a different temperature, but it's not the case that all of them can be useful for when it comes, specifically when it comes to dynamic testing. We did only static testing, but we wanted to extend this to dynamic testing. So we couldn't do any XRD, but just the explanation comes from the literature. And in conclusion, what I can say is just, again, for example, the recrystallization and grain growth is one of the reasons of what we saw in the UTS and hardness, reduction in the dislocation density within the microstructure, also reduction of the residual stresses in some cases. So there are residual stresses because of the heat process, right? Additive manufacturing, in additive manufacturing, everything is about heat. It's about the melting over there. And we know that because of that, there are residual stresses. And what's the level of the residual stresses? Is it tensile or compressive? Of course, we didn't do any measurement. I cannot say anything about our cases, but from other works, I can say that there are all this, right? Or under tensile or compressive, and each one of those affect the part macromechanical behavior. And also homogenization of a more stable structure when we do heat treatment. That happens specifically when we have single phase, austenitic phase in stainless steel 360 now. And yeah, and the future is going to be doing the investigation using XRD. That definitely we have to do that. And also evaluating an annealing time and also annealing temperature, for example, the different like the rates in the cooling as well. So to see the effect of that on the final mechanical property. Yeah, thank you very much.